Okay, now electric field has a lot of similarity to gravitational field that you guys have learned. You will talk about gravitate like last time under the gravitational field chapter. You guys remember that some of the main quantities that you talk about would be like gravitational force, gravitational field strength, the GPE, sorry, the GPE value U, the GPE value U, and then after that the potential phi. Now, under the chapter of electric field, you have something similar also. You will notice that the bulk of the chapter also tends to talk about these very same quantities, but applied for electric field. You will be talking about electric force. You'll be talking about electric field strength. You'll be talking about electric potential energy W. Then you'll also be talking about electric potential B. Okay, you'll be talking about similar quantities. Okay, so from there you will notice that a lot of the quantities that you're defining for electric field is similar to gravitational field. The form of the equation, the form of the definition is very similar. The only thing that you have changed is that you change the term from mass to charge here. Gravitational field, you know that it only affects mass. And then electric field, you know that it only affects charge. So when you go to electric field later on and you see the equations and definitions, you notice that the only thing that really changed is changing the whatever you use for mass to charge only. Okay, right. So let's start it off with electric field. Now, electric field A2 is a continuation for electric field AS. Some of the things here that you learn, some of the things here is actually from your AS. Now, in AS, we ask you what is actually meant by an electric field. We told you that electric field is just simply a region where a force is experienced by an electrical charge. Okay, and then after that, we also subsequently told you that when you want to determine the direction of when you want to represent an electric field visually, you use field lines. And then when you're talking about field lines, there are certain things that you associate with the field lines, namely the direction and also the spacing of the field lines. When you want to represent your electric field visually, you use field lines, and the direction of the field line and the spacing of the field lines will tell you something about the field itself. So if, say for example, I want to talk about the direction of the electric field, what we'll know is that the direction of the electric field is actually determined by following the direction of force acting on a positive test charge. If this is a electric field of charged parallel plates, how do I know what is the direction of the electric field here? This one, if you put a positive test charge, you know the positive plate here will repel the positive charge. The negative plate here will attract the positive charge. So in general, your electric force on this positive test charge is here. So you know that your electric field therefore must be here, following the direction of force acting on the positive test charge. If you have two isolated charges, one being a positive isolated charge and one being a negative isolated charge, if you want to determine its direction, again you determine it based on the direction of force acting on the positive test charge placed in the field. If I place a positive test charge here and I place a positive test charge here, positive and positive will repel, so the Fe from the positive test charge is here. So the direction of my electric field is outwards. Positive and negative will attract. So the direction of the electric field on my positive test charge is going in this direction. So the direction of my electric field is inwards. Okay, in general, that is how you determine by definition. But you guys probably have another way of doing it where you always say that, yeah, the field line must always be from positive to negative. For the field line will always be coming out positive, the field line will always be going in for negative. That is actually not wrong, it's also correct. But the main reason why how we determine it is actually based on the direction of force acting on the positive charge. Okay, and then after that, we also mentioned to you that the spacing of your field lines actually tell you about the strength of the field. Okay, so what we mentioned to you was that when you have field lines closer to each other, that would have meant that the field strength is stronger. Okay, same like in your gravitational field chapter, we tell you that if you're talking about the spacing of the lines or the gravitational field lines, the closer the lines, the stronger the field. The further apart the lines, the weaker the field. You apply the same concept here for electric field. If you see that the lines are closer to each other, the field will be stronger. And then you see that the lines have equal spacing, we will say that the field is uniform. Okay, constant field strength. Okay, so that's in general what we will normally say for electric field. This is just an introductory part. Okay, so wait on. Is there anything I need to say here? The closer the field lines, the stronger the field. If you want to, you can say vice versa and vice versa. Meaning to say, if the lines are further apart, the fields are weaker. Then after that, uniform fields between charge particles have equal lines of equal spacing. Therefore, constant field strength. Okay, if anything you want to add, probably you can just add this. All right. Now, then we go to the main part of your chapter. When you want to determine the force acting on a particular charge, there is one specific equation to use, okay, which is described by Coulomb's law. Say for example, right now, I give you two cases where I have two charges. I have a positive and negative charge, and I have positive and positive charge. Now, for the positive and negative charge, both of these charges will experience a force of attraction. For the positive and positive charge, both of these charges will experience a force of repulsion. Okay, I'm interested in finding out what is the force acting on the charges. Okay, so if I look at the first case here, which is this one, whatever force is being experienced by positive large Q will also be the force experienced by the small negative Q because of Newton's third law. Newton's third law, you learn that when two objects interact, they exert equal opposite forces on each other. So you could say that this charge is experiencing an electric force due to this charge. Likewise, this charge is experiencing electric force due to this charge. So they are actually interacting with each other. The forces that they exert on each other will be equal and opposite. So when you're talking about the electric force, if you find the force here, there's also the force here. Okay, they are one and the same because of Newton's third law. All right. So if you look at the second example, it will still be the same too. Whatever electric force you have here will be equal and opposite to the electric force here because of Newton's third law. You find one, you'll be able to find the other also. Okay. Now, if I want to find out the magnitude of the electric force, there's one particular law that you refer to, which is Coulomb's law. Okay. Coulomb's law tells you that the force between 2-point charges is directly proportional to the product of the charges and inversely proportional to the square of their separation. Okay, so what this means is that if you read it as it is from the statement, that means that Fe is proportional to product of charge, Fe is inversely proportional to the square of their separation, the separation being this R here. Okay, so if you combine this one and this one, you get Fe is proportional to QQ over R squared. Now you want to get rid of the proportionality sign here. So when you want to get rid of the proportionality sign here, you introduce a constant. Okay, just a random constant K. This one is not the Boltzmann constant from ideal gas. It's just another different constant. All right. Now the constant k here is actually 1 over 4 pi epsilon naught. Okay, this is actually the real expression for the constant 1 over 4 pi epsilon naught. Your electric force between 2 point charges is actually going to be given by this. Okay, notice the similarity with gravitational force. Gravitational force was gmm over r squared, right? You notice that here is product of charge divided by separation square. For gravitational force, it is product of mass divided by separation square. And then after that, both of them have to be multiplied with a certain value. For gravitational force, you multiply with gravitational constant. For electric force, you multiply with 1 over 4 pi epsilon naught. Okay, the similarity you see is here. It's like you're just changing out the mass to charge. And then whatever quantities that were related to mass, you change it along to represent for charge too. Okay. Now the 1 4 pi epsilon naught, there's a symbol here called epsilon. Okay, you see this symbol. This one here is called epsilon. It's a Greek letters epsilon. This one here is called epsilon naught. Okay. Now epsilon naught is just simply permittivity of free space. Okay. When you look at permittivity, this one here is what we call as permittivity. All right. Permittivity is just simply how easy it is for an electric field to pass through a medium. That's all there is to it. Okay. It measures how easy it is for an electric field to pass through a medium. Say maybe you want the electric field to pass through rubber, metal, wood, stone, etc. So depending on the medium, how easy it is for a electric field to pass through it will vary. The epsilon here is a constant called permittivity. It measures how easy it is for a medium to pass through a medium. When you see the term epsilon naught here, this one here, this one actually refers to permittivity of vacuum. What is the permittivity value of vacuum? How easy it is for an electric field to pass through a vacuum? That's all there is to it. Permittivity of vacuum, you actually have the values already. It's actually under the front page of your question paper. Your data sheet, they've given you the value of epsilon naught, permittivity of free space. Free space is vacuum. Okay, permittivity of vacuum is actually permittivity of free space. Okay, they've given you this value, and then after that, they've also given you an expression. If you want to use 1 over 4 pi epsilon naught, rather than you substituting in all the individual values, they've already done it for you, and they're telling you this is the value. Okay, in your calculation, when you want to use 1 over 4 pi epsilon naught, you can actually just use this straight rather than substituting in the individual values. Okay, right? So for permittivity, you don't really need to bother so much about its meaning or what's its significance. Your exam does not ask you that. They don't really care about that. They just need you to know that in using the equation for electric force, there's this symbol epsilon naught. Where can you find that value? Where can you find the value of that constant? Okay, that is all there is to it. And then after that, there is one thing here that I need to mention. Now, the case here when you're talking about Fe equals to 1 4 pi epsilon naught. Let me just use a different screen here for you. Now, the 1 over 4 pi epsilon naught QQ over R squared. This one is only applicable for point charges. Okay. Now, Point charges would just be something like this. This one and this one. These are what you call as point charges. They have no volume, no size. It's just a point with a charge. Okay? But a lot of times you see that in your questions, you may not necessarily have a point charge. You may suddenly have a charge sphere instead. You may suddenly have a charge sphere, or you may have something with something random like this that has size and volume. This one here has size and volume, therefore is not point charge. Okay, this one also has size and volume now. Okay, now specifically what I want to highlight is this. This one by right, when you want to use Fe equals to 1 Fe equals to 1 over 4 pi epsilon naught QQ over R square, we tell you it is strictly speaking only applicable for point charges. But later on when you do your questions, especially later, you'll notice that we don't use point, we're using a sphere. The question tells you that you have a sphere, okay? The sphere has size and volume here, but somehow or another, we were still able to use this equation. When this equation in the first place says it's only applicable for point charges being this one here, it's just a point with a charge. It should not have, it has no size, no volume to consider, but somehow you were able to use it for charge spheres. Now, this is where you need to make a distinction. What we'll tell you now is that charge spheres is equivalent. Charge spheres can be considered as point charges because their field appearance is the same. Charge spheres can be considered as point charges because they have similar field appearance. Okay, because they have similar field. Okay, similar field lines. Okay, I think I better change this. They have similar field lines. Okay, charge spheres can be considered as point charges because they have similar field line. Why do we say that? You say for example, this is a point charge, a positive point charge, no size and volume to consider. If I want to draw out the field lines around a point charge, the field lines around a point charge would be like this. Okay, it's radial and it will be pointing outwards. If I have, say, a charge sphere and I ask you to draw out the field line of a charge sphere, you'll notice that the charge sphere has a field line similar to a point charge. Wait, let me just draw this out. Say this one is a charge sphere. Right now I have a sphere. Okay. This one has size, this one has volume. If I want to draw out the field line around a charge sphere, you will notice that it looks like this. Okay, so one of the things you learned under your AS also was this, isn't it? Field lines must always be perpendicular to the contacting surface. Okay, it must always be perpendicular to the contacting surface. So when I wanted to draw the field lines around a charged sphere, I know that the field line in contact with the surface must in the first place always be 90 degrees with the surface. Okay. Now for a sphere, if you cut it in half, the cross-sectional area is going to give you a perfect circle. Okay, it's going to give you a perfect circle. When you cut a sphere in half, the cross-sectional area is going to be a circle. Then after that, when you combine the fact that field lines are always perpendicular to the contacting surface, you get this pattern here. Okay, this causes the field lines to be radial for a sphere. Okay, now there's one thing here that you can also see. Since the field lines are radial, if you extrapolate the line in, this is what you see. Okay, if you extrapolate the lines on the surface, you will notice that the lines after being extrapolated, they will all appear to come from the center, isn't it? So here is where we then start to say that the charge sphere can be thought of as being similar to a point charge because the field lines for a charge sphere appear to originate from the center, just like a point charge. So in your case here, we could actually say this now. Charge sphere is identical to point charge, identical to point charge as the field lines appear to come from the center. As the field lines appear to come from the center, just like a point charge. Okay, so that's why here we can say that if you're considering charged spheres, you can say it's actually equivalent to a point charge because by looking at the field lines itself, it is similar to a point charge. Okay, the point charge for point charge, the field line is radial and it comes from one point. Charge sphere, the field line is also radial. It also appears to come from one point. Okay, this is one key fact here. Charge spheres can be considered as point charges. Then the other thing here we can also tell you is this. This one is the second fact. The second fact here is this. Non-uniform objects, non-uniform charge objects can be considered as point charges if their separation is very large when compared to their size. Okay, so the other fact here you needed to know is that if you have a non-uniform objects, irregularly shaped like this one here, you can only consider that as point charge if the separation is very large. Okay, now how do I go and make sense of that? All right, this one I will have to, I'll have to rub this one off. Okay, now say for example I have a object that looks like this. This one is clearly not a sphere, is clearly not a point charge, right? Okay, and then I say that this is one charge object, and then this is another charge object. Then you consider this one. The separation with relation to the size, this one is small separation. So this one not considered as point charge. But say for example right now, I tell you I take these two same objects which are non-uniformly shaped, but I increase the separation a lot such that it now becomes like this. This one is now, I bring it up here, this one is now positive, and then the other one, this one here on the right, I bring it here like this is positive. Now then after that you look at the separation now. The separation is very, very large, isn't it? This one here and this one here. If I draw a very large exaggerated case here, this one here is considered to be large separation. So this one I can say therefore considered as point charges. Okay, so in the event that you have a non-uniformly charged object, it's not a sphere, you can also consider that as point charges if you see that the separation with the other charge is very large in relation to their size. Okay, so there are two ways in which you can consider something as point charge. Either is a charge sphere or either the separation is very large. When you have either this case satisfied and this case satisfied, you can then say you can use this equation. All right, because now you've proven that they're point charge, therefore you can use this equation. All right, so this one I save first in the diagram. Eventually I'll just put it inside the recording in Google Drive also, so don't worry. The screenshot of this one is also will be in Google Drive later for the video recording. Okay, so back to the question here. The reason why I'm explaining this to you is because of this statement here. Charged objects only approximate to point charges when the separation is large or if they are perfectly spherical. So in these two cases, you can actually use Fe equals to 1 over 4 pi epsilon naught Q over R squared. That's the reason why I just explained is to explain further why do I say this. Okay, so that one is for electric force. Then the next thing I just want to talk to you about is electric field strength. Okay, now electric force is one thing. Sometimes I'm also interested in knowing how strong is the field at a particular point in the electric field. Okay, that one is what you call as your electric field strength. Now, electric field strength in A2 is the same as your electric field strength in AS. It is just simply the force acting per unit positive charge. Okay, E is equals to Fe over Q. This is from your AS. But you also learned just now that electric force can be represented as 1 over 4 pi epsilon naught QQ over R squared, right? What if you sub this one inside here? You will actually get a new expression. Since electric field strength is Fe over Q, you sub in the field strength value, electric force value, you're going to get this instead. The Q and Q here will cancel off, giving you this. So now you actually have two separate equations for electric field strength. You will have E equals to Fe over Q. E equals to 1 over 4 pi epsilon naught QQ over R squared. Alright. Now, when do you want to use this or this depends on the context of the question. It depends on what has been given to you inside your question. Now, you notice that in both equations, you have a Q expression for Q, right? There's a small q at the bottom and a big Q at the top. The small q at the bottom is actually the less important charge, which is actually the test charge. The big Q here is actually the more important charge, which is actually the charge producing the field. Okay, so say for example right now I try to apply to this field here that you have. This one here is one positive test charge sorry, not one positive test charge. This is just one isolated charge with positive value is producing an electric field around it. And then after that, I tell you I'm interested in the electric field strength at this point. What is the electric field strength at this point? So if you want to find the electric field strength at this point, you could have used this equation. You can also use this equation. If you have wanted to use this equation, what you would have to do is that you will have to put a test charge here. You have to put a positive test charge here. And then you have to find out what is the electric force acting on the positive test charge. Maybe this one I'll write it here, I think. Okay, you put a positive test charge here, Q. In your case here, if you want to find out your electric field strength, it will just be E equals to Fe over Q. You place a test charge here, you find out what's the electric force acting on it, then you'll be able to work out what's the electric field strength at that point. It'll just be the force acting on the test charge divided by the test charge itself. Okay. Then the other way you can also find out what's the field strength here is by using this. Now, this Q here, as I mentioned to you, is actually the more important charge. It's actually the charge producing the field. That one is this one here. This one is your big Q. And then after that, if you know the distance that you're trying to test, which is this distance R here, you want to find the electric field strength here at this point, you can just use E is equals to 1 over 4 pi epsilon naught Q over R squared. Okay, so both ways will still give you the same answer. It's just a matter of what you are given in the question. Only then will you be able to determine whether should you be using this or whether should you be using this. Okay, that is electric field strength. Okay, so far so good. Right, so I think we better just take a short break. I'm done with this part. I will just go through the questions later. Now it's 3:42 p.m. We will resume at maybe 3:50 p.m. Just take maybe less than 10 minutes break. Okay, so we'll resume at 3:50 p.m. Okay, so just take a short break first. Okay. Okay, right. So let's continue. Okay, before I go to the past year question example, there's another thing I just like to highlight to you for electric field strength for your case here. Now, electric field strength is Fe over Q, force per unit charge. If you try to see some similarity with your gravitational field strength is force per unit mass. You see the form of the equation is again very similar. All right. And then after that, when you look at the other definition for electric field strength being 1 over 4 pi epsilon naught Q over R squared, this one is your constant, right? And then this one is your charge in distance. When you're talking about gravitational field strength, you will notice that the form of the equation is again similar. You would have your mass divided by separation squared, and then you would have to multiply with your constant again. Okay, so you see the form of the equation that it follows a certain pattern to it. So in general, if you're able to memorize the set of equations for one chapter, doesn't matter whether it's electric field or gravitational field, you should be able to easily reproduce back the equivalent equation for the other field. Okay, so just see that there is a similarity here. Okay, right, so if nothing else, go to page 13 of your worksheet. Can you just go to page 13 of your worksheet? I'll just go through that with you. Have a look at page 13 of your electric field and capacitance worksheet. So we'll go through this one first. Okay. Okay, this one is June 16 P42. Okay, sorry, I opened the wrong paper. Have a look at June 16 P42. So this one is question 6. They're asking you by reference to electric field lines, explain why is it that a charge sphere can be assumed as a point charge. This is similar to what I've just explained to you. Okay, right? Why is it that when you're talking about spherical conductors or charge sphere, the charge can be considered to act as a point charge as this center? Why can you consider a charge sphere as being similar to a point charge? So as I mentioned to you, in general, if say you have a sphere, you cut it in half, is a perfect circle. Then after that, when you want to draw the field lines around that circle, the field lines would always be perpendicular to your surface. And then after that, when you go one step further and try to extrapolate the line, you will notice that it appears to come from the center, much like the case for a point charge. For a point charge, the field lines are radial and they come from one point. Your charge sphere has a similar appearance. Okay, so you can write any one of these answers, the ones in red or the one in mechanical pencil, where they say that the field lines are radial and appear to come from the center. Hence, it can be considered to act as a point charge because the appearance here is the same as this one. Okay, right. The one thing here you need to be careful about is when you say the field lines come from the center, the field lines itself is not actually coming from the center for a charge here. It appears to come from the center. So hence the term here, they say appear. Alright, so when you write the answer for this kind of explanation, please be careful that this one is appear. Okay, this is the keyword. Alright. If you want to write it in another way, you can say something like this. Field lines are always perpendicular to the surface of the sphere and appear to come from the center, hence it can be considered to act as field lines. Exactly the same thing as this now. What I did was that just now I told you field lines will always be perpendicular to the surface. That's why the field lines look radial, and because of that, the field lines appear to come from the center. Therefore, you can consider to act as a point charge. That is actually the full story now, from 1 to 2 to 3. But the question just requires you to have either 1 or 2 before you follow up with 3. Okay, it depends on you now. Okay, you can explain based on your understanding. All right. So this one you're fine. Then I can just move on to the other one. You're okay. Right. So this one I'll just rub it off. Okay. So this one is here. Okay. So the next question you'll be doing is this one. They tell you there are two isolated protons that are separated in a vacuum by distance x. Find out what is the ratio of the electric force between the protons as well as the gravitational force between the protons. So what you essentially have now is something that looks like this. You have two protons. Okay, the two protons say will be here. There's one proton here and then one proton here. Okay, and then they're separated by a distance of say r, for example. Okay, now the proton has a mass, so therefore it will have gravitational force. So your protons here, it will experience gravitational force like this. Okay, because it has mass. But at the same time, because your proton is positively charged, this is positive, they will experience electric force. But the direction of your electric force will be like this. This is your Fe, and then this one is your Fe. Okay, they just simply want the ratio of the electric force between the protons and the gravitational force between the protons. So this is just a simple exercise in you applying the equations. Hg is g m over r squared. Fe is 1 over 4 pi epsilon naught q over qq over r squared. All right. So you're just trying to apply in your case here like this, and this is what you get. Okay, here I just wrote in another way like q1, q2 is actually qq itself. Now you notice that because they are two protons, right? They actually carry the same charge. Okay, so I can actually say that this one has charge q, this one has charge q. They're actually the same charge, so it will become q squared. All right, and likewise I can also say that because they are the same object, they have the same mass. This one will have mass m, this one will have mass m. So if I use gmm over r square or gm1 m2 over r square, it's just gm square over r square. All right, because they have the same mass, so it's square. They have the same charge, so it's square. All right, then after that I want to take one over the other. Fe over Fg, ratio of Fe over Fg would be this one divided by this one. Okay, now here, even though you did not know what is the value of R, is not a big issue because your R will cancel off. The R of Fg will cancel the R of Fe. So this one will cancel, this one will cancel off, eventually giving you Q square over 1/4 epsilon naught Gm square. I mean, if I want to rewrite it for you properly, this one will be 1 over 4 pi epsilon naught q square over gm square. This is just one way of rewriting the same thing. Okay, so then what you just need to do now is you just need to sub in the value. Okay, now charge over proton is carrying a charge of proton is actually plus E, right? That means it is 1.6 times 10 power minus 19 Coulomb. Okay, how about mass of a proton? Mass of a proton you can actually get it from your front page of your data sheet. I can just show it to you here now. You can see that in your data sheet, in your exam paper, there is actually mass of electron, and then just right below it is mass of proton. You can actually find out the mass of your proton from your data sheet. Okay, so in your case here, the mass of proton is just something that you need to find from your data sheet. You don't need to remember what was its value, just know that it's from your data sheet. So in your case, the mass of your proton is 1.67 times 10 power minus 27 kg. Okay, so you just sub in the values, eventually you get the answer as 1.24 times 10 power 36. Right, so this part is fine. So far so good with this. All right, okay, then if you're okay with that, yeah, just be careful to remember to square your values. A lot of times people do the questions, they remember to multiply and divide those things, but they forgot the squares. So please make sure you don't forget where your squares are. All right, here I actually put in all the individual values for 4 pi and epsilon naught. Just now I mentioned to you, you can actually simplify your working by just using the expression for 1 over 4 pi epsilon naught straight. So you can do it like this, or you can do it like this. But my preference would be to use this now. Just make sure you know how to identify this. Right? Okay, now by reference to your answer in 1, Suggest why gravitational forces are not considered when calculating forces between charged particles. Now, right now, as I mentioned to you just now, you have your proton here, and then you have your Fg, and then you have your Fe and Fe here. So the question is basically just asking you this. When you're calculating the forces acting on a charged particle, why is it that you don't consider gravitational force? Now you can see just now in your question, Fe over Fg is 1.24 times 10 power 36. This is telling you that your electric force is 10 power 36 times more than your gravitational force. It's actually telling you there are 36 zeros. Alright, this is bigger than this, and there are 36 zeros behind the number. So your electric force is actually very, very much larger than your gravitational force. So therefore, you don't consider the gravitational forces. Since the ratio of Fe to Fg is 1.24 times 10 power 36, the electric force is very much larger than gravitational force. Hence, the gravitational forces are not considered. Okay. You have to refer to the values that you have found in part 1 to do this. Okay. So if page 13 you're okay, we can move on to page 5. Okay. We can move on to page 5. So if you're okay with that, just have a look at page 5. Right, so have a look at page 5. Page 5 is November 15 P41. This one is question 5. Also question 5. Okay, so have a look at that. Okay, now, if you look at page 5, they told you right now that charge particle P is situated in a vacuum at distance x from the center of a charged conducting sphere of radius r as illustrated in figure 5.1. The particle P is outside the conducting sphere, and the charge on the sphere may be assumed to be a point charge at its center. Now state what is Coulomb's law. Okay, so this one here, as I mentioned to you, Coulomb's law explains to you the electric force between two charges. Now this one here, I wrote something where magnitude of force between 2 point charge, the distance r apart is directly proportional to the product of the charges and inversely proportional to the square of the distance apart. This one is actually a very long way of writing the same thing. You can actually just follow back what is written in your notes, where we tell you that the force between 2 point charge is directly proportional to the product of the charges and inversely proportional to the square of the separation. This one is a very short way of writing the same thing. If you're asked to write what is Coulomb's law, you just use this. Force between 2 point charge is directly proportional to the product of the charges and inversely proportional to the square of the separation. Now when they say, if you look at the question just now, it has 2 marks to it. Where did your 2 marks come from? Your 2 marks actually came from here. If you say directly proportional to product of charge and inversely proportional to square of separation is 1, if you specifically mention point charge is where your other point comes from. Okay, this point is actually quite important to have. Right, you must mention that. Alright, so just take maybe some time to copy that, then after that I'll move on to the other question. Okay, so I think this one should be okay. You just copy it. Then I go to the next part. Now they tell you the sphere and particle P are both positively charged. State the direction of force acting on particle P. So now you have the sphere that is positive and you have particle P that is also positive. They ask you what's the direction of the force acting on particle P. So as you know already, positive and positive will tend to repel, right? You're talking about particle P, the electric force should be like this. So what is the direction of the force? You will say it is force to the right or force radially away from the sphere or to the east. Okay. Now you should not write this answer though. If you say that the force is away from the sphere, it could actually mean something like this. Let me just draw a separate line. Because in the case when they say force away from sphere, they could have understood it as something like this, something like this, something like this, something like this. Alright, when you say away from the sphere, it's a bit vague. It doesn't necessarily mean a straight line horizontal like this. It could mean the diagonal lines here. So this one here, they don't accept. Because it said away from sphere, it could mean this, this, or this. So it would be better if you just write force to the right, or radially away from the sphere, or to the east. Okay. Then after that, where do you suppose is the position for particle P for the force F to be maximum? Okay, now, as I mentioned to you just now, if you have a charge sphere, they can be considered as a point charge, right? Particle P itself is already a point charge, okay? Sphere is also considered to be a point charge. So if I want to find out the electric force here, these both being point charges would mean that I can use 1 over 4 pi epsilon naught QQ over R squared. Now here you can see that what's the relation between Fe and R? From here you can see that since Fe is equals to 1 over 4 pi epsilon naught Q over R squared, if R drops, that means Fe would increase. The closer the separation, the smaller the separation, the bigger your electric force. Okay, in general, or common sense will tell you that because these are both repelling, the closer you move them towards each other, the stronger the electric force. This is from what common sense will tell you, or you can also deduce it from your equation. So you know that it will become stronger the closer you move them. But where is it going to be maximum? It's going to be maximum right at the surface. If you move this all the way to the surface, the force there will be maximum. Or when your separation is equals to the radius now, okay? You can just write when force is maximum at the surface of the sphere. Okay. So the choice of unsuitable answers to you again will be near sphere. Near sphere does not necessarily mean that you are on the surface itself, could be somewhere a distance away, a short distance away, so this one cannot. Next to sphere also cannot, because next to sphere does not necessarily imply you're on the surface. It could be that you're some distance away, you're actually still next to the sphere. So this one also you cannot use. So the most descriptive one would be at the surface of the sphere. Okay. So this one should be okay. Right. And then the other thing now they want you to do is this one. Now, determine the ratio of force of particle P at x equals to r and when x equals to 4r. Right. Okay, now I think this one I need to change again the diagram. Okay, now your diagram, I think I use this one. Your charge sphere is this one. Okay, your charge sphere is this. Your particle P is this. This is positive. This is positive. This one could be considered your big Q. This one could be considered your small q. Now your question wrote the separation as x, okay? So if taking that into account, your Fe is actually 1 over 4 pi epsilon naught QQ over x squared. Now you will notice that sometimes I write this as R, sometimes I write this as X. They actually mean the same thing. It just means the distance between the charges. It's just that for some cases, the question likes to write it at another variable. In their case now, the separation between the charges is X. And then R refers to the radius of the sphere. Okay, so don't get confused with the notations here, because previously I wrote here 1 over 4 pi epsilon naught QQ over R square, right? The R is referring to the separation between the charges, but here in your question, the R is not referring to separation of the charges, it's referring to the radius of one of the charge. The separation between the charge here for them is X. So this is the correct form of the equation you should use. Okay, so they're asking you right now to consider the force on particle P at these two different distances. So the force on particle P, as I mentioned to you, because these are now considered 2-point charges, you can use Fe equals to 1 4 pi epsilon naught QQ over x squared. They want you to find it at two different distances. One is when it is at 4r, and then another when it is at r. This and this, you can still use this. Alright, so you want to use ratio right now. You must first identify what is common for both of the cases. Now you notice that for both of the cases, only the distance is being changed. Everything else remains the same. The constant, needless to say, it will still be a constant. The charges that you're using is also still the same. So everything else being the same, only this and this will be different. So I can say that Fe is inversely proportional to x squared. Then what I'll do is Fe1 over Fe2 is equals to x2 square over x1 square, right? Then after that, you get this ratio. The case number 1 is this one. Case number 2 is this one, right? So you sub it in, you get 4r square over r square, you get 60. All right, so that is one small part of your electric field chapter. Okay, right? So this one is okay. Then after that, I move on to the next one. Okay, so let's move to the next one. Okay, now they tell you right now, when the charge on the sphere is 6 times 10 power minus 7 coulombs, the electric field strength at the surface of the sphere is 1.5 times 10 power 6 volt per meter. An electrical background, a spark, will occur when the electric field strength at the surface of the sphere exceeds 2 times 10 power 6 volt per meter. Find out the additional charge that may be added to the sphere before electrical breakdown occurs. All right. Okay, now what does the electrical breakdown here actually mean? Now you consider this one first, because they're not talking about the sphere. Let's just explain for the spheres first. Now for the sphere right now, they tell you the charge on the sphere is, maybe I should just draw it here like this. This is your original sphere. They tell you that your charge on the sphere is 6.0 times 10 power minus 7 coulomb. And then they also told you that the field strength at the surface of the sphere is 1.5 times 10 power 6 volt per meter. Now, the part where they mention electrical breakdown occurs when the electric field strength at the surface exceeds 2 times 10 power 6 volt per meter. Find the charge that may be added to the sphere before electrical breakdown occurs. Now, in the first place, what is electrical breakdown? Let me just explain this to you. Electrical breakdown is this. They say that when your electric field strength exceeds 2 times 10 power 6, you consider the case now where the field strength at the surface is 2 times 10 power 6 volts per meter. They say a spark will not occur when your field strength is at least this value. What is actually happening here is this. You see, your sphere is surrounded by air. You can consider the air as consisting as a positive nucleus and negative electrons orbiting around it. Let's just say this is a simplified assumption. You have a positive nucleus and negative electron. This one, your charge is 6, you carry a certain charge. Say this one is positively charged. Now, this positive charge will interact with this positive nucleus. It will also interact with this negative electron. They will both experience electric force. What will happen is that the nucleus will experience an electric force this way. The electron will experience an electric force this way. You can see that they are actually opposing each other. Nucleus wants to be repelled out, electron wants to be drawn in. Now, you know that E is equals to Fe over Q. Fe is proportional to E itself. Okay, Fe is proportional to E. If your E increase, your Fe will increase. Now, here, at this case here, what you're actually saying to you here is that when your E here is this value, your Fe is strong enough that the electrons are stripped away. This one what we mean here is that at electrical breakdown, the Fe is strong enough to strip the electron from the air molecules. Okay, so your E becomes strong enough. Here it was originally this value, then you increase it to this. When you increase it from this to this, you're causing the Fe to increase. The Fe will increase up to a point where it is strong enough to strip the electron from the air molecule. Okay, the flow of electron that you then see, if your electron is stripped off from your molecule, the electron will not move like this, right? Okay, the flow of electron is what is seen as spark. Okay, what we'll tell you is that the flow of electron is seen as a spark. That's what this one is telling you. Electrical breakdown, spark occurs when field strength at the surface exceeds 2 times 10 power 6 volt per meter. You're actually changing this to this. When you have that, the electric force acting on your air molecules is strong enough that electrons are stripped away. So when the electrons are stripped away and it moves towards here, that's what you see as a spark. Okay, that's the basis of this thing. But they're not really asking you to explain that. They're just asking you to explain to us what amount of charge do you need to add to the sphere before your electrical breakdown occurs. Now this one is positively charged, this one is positively charged. Originally your Q1 is 6 times 10 power minus 7 Q. Now what we want to know is what is the additional charge that you need to use. How much additional charge do you need to add to this so that you reach this? Okay. Now your charge here will affect your field strength because E is equals to 1 over 4 pi epsilon naught Q over R. Q will affect E. So the more charge you add in here, the more your electric field strength will become. They're interested in finding out what is the additional charge that you need. So you can use E is 1 4 pi epsilon naught Maybe I'll write this out for you. 1/4 pi epsilon naught q over x squared. I'll write this out easier for you. Now, what is the same here throughout the process? I could say that the x is constant, right? What's the distance I consider? I consider the distance from the center of the sphere to the surface of the sphere. Okay? Because right now, you did not change any distance. You're still considering from the center of the sphere to the surface of the sphere. Okay? Your x is still the same. You're using the same sphere. You're considering the same point. So your x is constant. X is constant. 1/4 pi epsilon naught is constant. So E is proportional to Q. So from here, E2 to E1 is Q2 to Q1. Your E2 is this one. E1 is this one. Your Q2 is what you want to find first. And then your Q1 is this one. This is the new charge that your sphere needs to have before electrical breakdown occurs. But the question is not yet complete because they say this. What is the additional charge that needs to be added to the sphere before electrical breakdown occurs? They're not asking you to find the final charge. They're asking you to find what is the additional charge. You want to find the additional charge, you take this charge minus this charge, and then you get your charge needed already. Okay? So that is one part of your questions that you can